Hi there. So in chapter 10, we're doing sections 10.1 and 10.2. Because we are going to be using the TI-84, we don't actually need to do this as two sections. We can do this at one because the graphing calculator is going to give us all the information we need for 10.1 and 10.2. So here's the idea of linear regression and correlation. So you're going to be given paired data, so like an x and a y, perhaps my height and then my weight, two numbers from each person. And the idea is to see if there is a direct relationship between those two sets. So for example, we're not doing this numerically, but just your opinion. What do you think? In general, is there a relationship between the weight and the height of a newborn baby? So in general, there is. Now, it's not going to work for every baby, but we're just trying to see in general. If the child is larger, so height is usually this way, but babies are laying down, so measure the baby this way. So if the baby is a big baby and very long, then most likely that baby weighs more. If the baby is very small, most likely weighs less. So yes, in general, there's a relationship. How about the size and the price of homes? If I stopped the sentence right there, I would say, no, not really, because you could have a huge house in the middle of Oklahoma. It's not going to cost that much. You could have a little tiny house in New York City, and it's going to cost a lot of money. But what if you were in one neighborhood? So you're just in one portion of one zip code, maybe like a 4 or 5 block area. Then is there a relationship? So with that one, once you narrow it down that way, yes. Basically, a bigger house is going to cost more. A smaller house is going to cost less. How about the hours of work and the income earned? Well, in general, I think I would have to say no. And you might think that I'm crazy, but it depends on if the person is paid a salary or did they get paid per hour. Because if someone's paid a salary, if there's some doctor that gets paid $200,000 a year and they only have to work 3 hours a day, well, there's other people that are making $10 an hour and they work 50 hours a week. But if you were talking about people that are paid an hourly income, then yes, there would be a relationship. More work means more money. So we're trying to see if there's a correlation. So correlation is just a fancy word to say relationship. Is there a relationship between the hours you work and the money you make? For most people, the answer is yes. But just because there is a correlation does not mean that we are proving a cause-effect relationship. So for example, I used to do this one a long time ago. If you would look at a country and see how many people you have to get together before you find somebody that owns a television, and then you look at the mortality rate, or you look at how long those people live on average. So there's a relationship, but does owning a TV make you live longer? No, there's no cause and effect relationship at all. But there's a relationship because if you're in a country where everybody has a television set, well, then they could probably afford good food, they could probably afford going to the doctor, etc. So we can prove that there is a relationship, but we can't prove whether it's cause or effect, at least in this section. Okay, so they're going to be given paired data, x and y, and the relationship is called the linear correlation coefficient. And, okay, don't get scared, but look at this formula. Yeah, that is a formula that I definitely do not want to do by hand. That is where I have my friend, the TI-84. But some facts about R that are important. It was made so that it always lands between -1 and 1. And it could equal -1, it could equal +1. I'll show you some examples in just a second. So R equals 1 means it's a perfect correlation. That means that if you were to graph the dots, they would go up in a perfectly straight line. And R equals -1 means the dots would be going down in a perfect linear pattern. That's called negative correlation. And if you get r equals 0, that means that there's 0 linear correlation or no linear correlation. Now look at these pretty pictures that I made. So this would be if r was like really close to a 1. So notice that the dots, they don't all land on the line, but they're very, very, very close. And it's going up, so that's positive correlation. If there's a general pattern that, yeah, they're going up, but they're sort of sloppy about it, that would be like an r equals 0.5. Now with r equals 0, there's two things that could happen. It could be there's no correlation at all, that they're just random dots, there's absolutely no relationship. Or it could be that it's something like a parabola or some other shape which we don't cover in this section. So that would be, no, it's not a linear correlation. And then negative correlation means that the dots are going down. So sometimes we use the word negative to means there's not something. Like if I have negative money, means that I don't have money. Well, negative in this case just means that the line is going down. It's got negative slope. Okay, so the R is going to be the test statistic. And like I said, in just a minute I'll show you. I've got the graphing calculator for that. In fact, I made a whole about 6-minute video just showing you how to use the graphing calculator. It's in the modules under chapter 10 about how to use the TI-84 for chapter 10. So you might want to watch that separately, where I take you step by step how to use the graphing calculator. So when we go to test whether there's a relationship, I just draw a line from -1 to 1 because R always has to be between -1 to 1. The critical values are going to be in table A5, which I'll show you in just a moment. The important thing is if R lands over here to the right in this region, that means there's a positive linear correlation. If the R is negative and it lands in this region, between -1 and the critical value, then there's a negative linear correlation. And if it lands in the middle, that means there's no correlation. So that could be the parabola, or it could be that they're just random dots that have no relationship. So suppose there was a correlation. So that would be like this, where there's a positive correlation, or like this, there's a negative correlation. Now, positive correlation means that as x goes up, y is going to go up. So if the x gets bigger, the y gets bigger. So that would be like somebody that works at In-N-Out Burger. The more hours they work, the more money they're going to make. With a negative correlation, that means as x gets bigger, then y gets smaller. So this could be something like, the more cigarettes that somebody smokes, the less years that they live. And these dots, that's called the scatter plot. And I'm going to show you on the screen in a moment how to get that, but also be sure to check out that video that I just said using the TI-84 for chapter 10. So finally, the equation of the line, which I drew in pencil right here, the equation for this line is y equals ax plus b. I realize that usually with lines we put mx plus b, but for some reason in statistics they call it ax plus b. All right, here's an example. So this doesn't have an application, it's just numbers that I made up so that I could show you how to do all the steps. So first of all, enter the information into the calculator using list 1 and list 2. So you need to put the x's in list 1 and the y's in list 2. Then, to make the scatter plot, see right here where it says stat plot? So you need to press second, stat plot, and the screen will look like this. Make sure that you turn it on, so put on, and then go over to this one with the dots for the scatter plot. Then use list 1 and list 2, so the x's are in list 1, the y's are in list 2, and then you could use whatever mark you want. This one is sort of hard to see because it's so small. I like to use the plus because it's positive. And then if you just go to zoom right here and zoom number 9, that will take you to the graph. And as you can see, these dots are lining up pretty well. They're not perfect, but that is a very good positive linear correlation. So then on my fancy piece of paper right there, I drew the scatter plot. So that's what it looks like. And by the way, if you go to trace and then use the arrow keys, it will jump from point to point and it will show you the actual numbers like 1 and 5, etc. The next thing to do is go to Stat, move over to Calculate, and then do number 4, the linear regression, and the line is going to be AX plus B. Next, it's just going to ask you, what are the lists? So X is list 1, Y is list 2. And after you press Calculate, it will then tell you the equation of the line will be 2.03x plus 3.394. And R is equal to 0.997. And we don't use the R squared in this section, so just the R. R equals 0.997. So that means that this almost lines up perfectly, but not quite a perfect 1.0. Pretty close though. Okay, then I need to write that down. So let me just bring my calculator back. So the regression equation, 2.003x plus 3.394, that part's right. N is equal to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there's the R. So here's table A5. It's the easiest one to use. All you need to know is what's alpha. So I'm going to use 95% level of confidence. So that means I'm using this middle column. And then also what's N. So N is 12. And then use the middle column. So the critical value is 0.576. So it's going to be a positive 0.576 on the right and a negative 0.576 on the left. And then just show where the R lands. So it lands way over here, close to 1. And that means that there is a positive linear correlation, which means as X gets bigger, the Y gets bigger. Okay, then on to an application. So this one right here, I actually found in a psychology book. So they have biological twins. So that means that they're identical twins. And this is a sad fact, but these twins were separated at birth. Maybe the parents got a divorce, maybe they put the twins up for adoption. It's sad, but it happens. So the twins were raised apart. So genetically, they're exactly the same, but they were raised in different environments. So is there still a relationship between their IQs? So they were just labeled as the IQ of one twin and then the other twin. And then, is there a relationship between the pairs? So I've got my, there's 13 twins here, so n equals 13. And I've got my table A5, so I go down to 13, and then over to the middle column. So the critical value is 0.553, positive on the right, negative on the left. And then I'm going to skip the part showing you all the steps because it's the same every time. So I went ahead and did that, and R turns out to be a 0.94, and the equation is going to be a 0.88x plus 12.93. So the R lands way over to the right, which means that there is a positive correlation, and this is the regression equation. So positive correlation means if going from 98 to 108, so this went up from 98 to 108, and this went up from 97 to 105. So as one of these goes up, the other one's going to go up. That's the meaning of positive correlation. All right, one last thing. So it might ask you to predict the IQ of the second twin if the first twin had an IQ of 110. Predict means that you're going to use the regression equation. Now, if there wasn't a linear correlation, then you just have to use the mean. So you just use the mean of list 2, and then that's your prediction. But if there's a Since there is a linear correlation, then you could use the equation. And substituting the 110 that was given right here for x, and then plug that in a calculator, and it predicts that the other one's IQ would be a 109.73. All right, so that is chapter 10.